Hi everybody, so we're going to introduce the law of conservation of energy, probably the heart and soul of this whole chapter. It is a complement to the law of conservation momentum, and hopefully once we get through the initial introduction and problems, you'll find that it's a whole lot easier to work with than anything we've done before. You just got to be able to keep track of the types of energy before and after an event. And we've already talked about the types of energy. It's really just going to boil down to kinetic or the two different types of potential, and perhaps some thermal energy thrown in the mix just to complicate things a little bit. So I'm going to do a quick review from the last one, set up some defined systems, because we've got to keep our mind on what system we're talking about, because there's subtle changes when you change systems. And then do some example problems using an organizing principle called energy bar charts. So let's get into it. So we learned before, anytime you do work, that process, you must change the amount of energy in that system. Okay, so let's talk about systems. And I'm going to talk about two systems that we can discuss. One I'm going to go with that is how do I want to say it, one we're going to want to use more often than the other. So if our system is just an object in question, a ball that's being acted upon, a car, any generic object, then the work done on it is always external to that object, because objects can't exert forces on itself. And so that work always goes towards some change in its kinetic energy, whether it's a positive or a negative change. In other words, it gains or loses kinetic energy. So for example, if I throw a ball and the only force acting on it is my arm, then that force is the same direction as the displacement. I do positive work, the ball gains kinetic energy. On the other hand, if I lift the ball up at a constant speed, there are two forces. There's an applied force, there's gravity, and so the net force on it is zero, so there's no work done, therefore then there's no change in kinetic energy. However, if I want to define my system as the object, the Earth, and then any potential springs, which we haven't formally introduced yet, but will come down the road, then any external work goes towards either kinetic energy, or now we can introduce gravitational potential energy or elastic potential energy. So let me explain in terms of lifting the ball. So if we're lifting the ball, then in our system is the Earth and the ball. Don't draw this. This represents the Earth. There's a reaction force due to the Earth, right? The ball pulls on the Earth pulls on the ball. So these, in essence, cancel out. In other words, we don't talk about the work done by gravity in that case when we include the Earth as our system. So the net work is just due to that, and it's just going towards gravitational potential energy, which we defined in the last tutorial. So it's a subtle difference, but it's a lot easier to look at these problems in terms of external work when we include Earth in our system, so that we don't have to worry about gravity doing work. We can just worry about something external to the object, like a person or a gun or something like that, a spring system. Or actually, if it's a spring system, we'd have to include the spring in our system to take away the work from that. And the reason we want to do that is because we can lead to this idea. If you have no more external work done on a system, then the total energy must remain constant. And that's a conservation law. That's huge. Okay? So if you leave something alone within your system, you can never change, add, or subtract from the energy. But what you can do is the forms of energy therein can transfer, or actually I'm going to use the word convert, from one form to another. So you can have an object yo-yoing, if you will, between potential and kinetic energy if it rises and falls when you define your system as the object and the Earth. There's nothing external to it. If something comes along and does work on it, then you're going to add to that kinetic or potential. So mathematically, what we can write this as is the sum, sigma, of our energy in a system equals the sum of the kinetic plus the gravitational potential plus any elastic potential if there's a spring involved. And those are the only three types of energies we really need to keep track of, and we'll talk about thermal a little bit. So if we expand this, what we can say is essentially before equals after. Total before. So I have a kinetic energy initial. I'm just going to write KE. I might have some initial gravitational potential energy. I might also have some elastic. Usually we only have one at the beginning of an event, but sometimes we can have two. You just got to understand where the object is. Is it above the ground? Is it attached to a compressed spring? Or just moving along a flat surface? That's not hard to keep track of. And so that just shifts to a different kinetic energy, or maybe a different gravitational, or maybe a different elastic. And then if there's friction, we'll throw in some Q that is lost. Okay, because generally thermal energy is going to go outside of our system to the ground, or whatever the object is rubbing onto. So that's, if you will, lost energy. So let's try to look at this schematically before we get into some numbers. So let's say I have a moving ball, all right, something got it moving some time ago, we don't know when, but it's moving. It's going down a hill, so that hill is important. And then we're going to take two cases, when there's no friction as it rolls, and there is some friction when it rolls. And so before we look at our energy transfer, we're going to look at them as like little pie charts. We want to define our system. And so to make our life easier, rather than define our system as just a ball, let's include the Earth in that. Okay, so at some point, work was done on a system to get it to this. We don't know when or where, but to understand that if a ball is moving and it's above the ground, something had to happen to it. We don't to give it that. But now we're interested in what happens after. So this is where we're going to pick up. So what type of energy do we have as it's moving? Well, it's going to have some kinetic. So we're going to assume that it has a small amount of kinetic compared to its gravitational potential. So why do we say it has gravitational potential? Because it's on a hill, it's above the ground, if you will, sea level, so it has potential energy. Now it's going to go down the hill. So when it goes down the hill, there is no external work done on it. Okay, gravity is not external because we define the system as the Earth, or the Earth is part of our system. There's no friction, so the ground is not external to it. So what that means is this whole pie must stay the same. The whole amount stays the same. We're not going to add or subtract from the energy. However, it's going to shift. Since we go downhill, we know we're going to lose potential energy. So our part of the pie that's potential, this one, is less than before. And where did that potential go to? Well, it just shifted or converted to more kinetic. Okay, that's the law of conservation of energy. We know that as it goes downhill, it's going to gain speed. So if it gains speeds, it has to gain kinetic. So the kinetic it gained is equal to the potential that it lost. In terms of mathematics, what we would say is the kinetic energy at the beginning plus the gravitational at the beginning, that's over here, has to equal the new kinetic energy, this one, plus the new potential energy. The sum remains the same. So if you know the velocity and you know the height, then you can figure out how fast it's going right there. Pretty easy. You don't have to worry about angle or forces or accelerations or anything like that. Now, if we throw in friction, it changes slightly. We're still dropping the same height we go downhill, so our new potential energy is still the same as the one up here. However, because of friction, we're going to lose, and technically we're losing this chunk of the pie to Q. Okay, so our pie is going to be that much smaller. And the amount of Q depends on the distance which you're rolling and the amount of friction, right? So if you recall from last one, that's just the force of friction times whatever distance you roll. So what's left behind in this last little wedge is your kinetic energy. And if you look at the area of this wedge compared to the area of this wedge, you know it's less. So we're not going to be going as fast, which is consistent with everything we've talked about from the law of motion standpoint. So let's now look at some other situations. And I'm going to just switch rather than to this little pie chart to bar charts, but it's really the same idea. Okay, so let's try to get as many done before in the 15 minutes, and I might extend it into another tutorial. So in this scenario, we have a block, and I've added information here that wasn't given. So add this information right here that's not given, and we have a mass of 1 kilogram. Okay, so our situation is we simply are pushing a block up an incline from point A to point B. Okay, and we are gaining speed. So we're not pushing in such a way that it's moving at a constant speed. It is gaining speed up that ramp. Okay, and that's what we can see. It's increasing speed right there. We are defining our system as the Earth block. Okay, so that's important. And it says to set 0 for the gravitational potential energy at A. So in other words, at A, we're going to call that point 0. In other words, our initial height, or y naught, is 0. Okay, so we want to look at how our energy shifts due to any external work and what it goes between. So let's ask ourselves, what are we starting with? So on the left column, we have before, during, that's while the work is being done, if any, and then after. So we have 3 choices: kinetic, gravitational potential, and spring potential. They're using PE for potential. Sometimes I do that, but don't let that throw you off. Okay, so we're told we have over here initial kinetic of 6 based on how fast it's moving and its mass. In fact, you could work out how fast it's moving using 1/2 mv squared. So I'm going to go up 1, 2, 3, 4, 5, 6 to represent 6 units of energy. So I'm just going to fill that in. Our gravitational potential is 0 because we're initially at 0 height, and there's no springs involved there, so it's 0. So we're starting with a total of 6 units of energy. So is any work done during this process? Well, you're given the information that the net force on the block is 4 newtons, so I'm taking the applied force and I'm subtracting the parallel component of gravity. And I'm multiplying by distance, so in other words, the work done is simply 4 joules. So we're going to add 1, 2, 3, 4 joules of work done during this process. I'm going to put a 4 there. So what that 4 joules of work is doing is it's going to add to our total energy. So the question is, what forms is it going to take? So we're looking at kinetic still, gravitational, and Q. There's no spring involved, so they didn't add that. So since it's a smooth surface, there's going to be no thermal. So the question is, where does that 4 go to? Well, what information do we have? Well, we're told that the change in height is 0.2 meters. So if we're lifting up, then that means we're adding. Some of that work is going to add to potential. And the potential energy, UG, is M, 1 kilogram, times G. We're going to say G is 10 to make life easier, meters per second squared, times a change in height of 0.2. So if I multiply those, I believe I get 2 joules. So we started with 0. We added 2 joules of potential. Okay, so we have to have 6 plus 4, 10 units of energy overall. That's the work energy theorem. So that means our kinetic must be 8. Okay, such that 8 plus 2 is, I don't know why I put PE there, that should be a 2. 8 plus 2 adds up to 10. And so what does that do for us? Well, if I know the kinetic energy is now 8, I'm not asking us to do this there, I can take that new kinetic energy and set it equal to 1/2 mv squared, and I can easily figure out how fast it must be moving at the end of the event. Again, I don't have to worry about angle. I don't have to worry about whether it was a straight incline or a curved incline, because all that matters is the change in height and the work done. That's really, really convenient. Okay, so I'm going to do another problem here. I'm going to stop the video and just make a new one so I don't get cut off on that one.